Hey everyone, here I'm going to be covering the visualization for insertion sort. So let's begin with the total code. Here I'm going to use my own swap function and I'm declaring it here, but here's the source code of it, just in case you don't remember, but I covered it in my last video talking about insertion sort. So let's start with our initial array. It's the same array from the previous video. It's 5 elements, and let's see the initializations of our indices for our double for loop. So we start off with int I is equal to 1 because here with insertion sort the assumption is that the very first element of the array is going to be our sorted part and the rest of it is going to be our unsorted. So we begin with I equal to 1 and j equal to 0, and I now is going to be the index that's going to join or grow as the inserted part of the array. So immediately I'm going to check, hey, if v of I is less than j, I'm going to swap. Is this true? Is v of I less than j? Yes it is. So I'm actually going to implement a swap, and I'm going to have I equals 1 become now part of the sorted part of our vector. So because in the previous j for loop I was only equal to 1, so when it incremented, j was equal to 1, right? In this previous one, j only stays in that place because once it increments is going to be equal to 1 and 1 is not less than 1. So we start again. Now our sorted has grown, our sorted part of the algorithm has grown by 1, and our unsorted is 1 less than it was before. Now with I is equal to 2, we're going to reset our inner for loop with j. J is going to be equal to 0. We're going to check if v of I is less than to v of j. No, this is not true. 14 is not less than 2. So we're going to iterate and increase j, and we're going to keep checking. So if v of I, which is 14, is less than v of j, which is 56, and here in this case is going to be true. So what we're going to do is that we're going to swap, and here, since j is going to continue iterating while it's less than I, this is going to be our final iteration. So now when we swap our two values here, our sorted part of our array has grown by 1, and our unsorted part of the array has decreased by 1. And we'll continue with the iterations. So I is going to continue to increase, but our j for loop is resetted. And now that I is equal to 3, v of 3, which is 9, is going to get inserted into our sorted part of our array. So we have our resetted for loop here of j. J got resetted, and we're going to keep checking. Is 9 less than 2? No. So we'll move on and increment j. Is 9 less than 14? Yes it is. So we're going to do a swap. And now with this, things are going to get interesting because when we look at this, we're going to increment j again, and we're going to see, these two elements are no longer sorted. But j is going to continue up until this last element. J is at its last element, which will let us swap and sort it, because here v of I, which is 14, is less than v of j, which is 56. We'll sort it, and now, right as our for loop for our iterator j resets, our sorted part of the array is sorted and has grown by 1. And now I is at the end of the unsorted part of the array, and j is reset, so we're going to find where we're going to insert 7 into our sorted part of the array. So we check if 7 is less than 2, which is not the case, and then we keep checking. Is 7 less than 9? Yes, this is true. So we're going to swap, and then we're going to keep checking. Is 9 less than 14? Yes. So we swap it. Is 14 less than 56? Yes, and we swap it. And this is how insertion sort works. As I keeps incrementing, that's what gets sorted. Right here, 9 gets inserted and shifted, and then 7 gets inserted, and everything else is kind of shifted, and it's all sorted. So I hope this clarifies how insertion sort works, and I hope this kind of makes more sense. And in the next video, we'll talk about merge sort, which is a better performing algorithm than insertion sort. I'll see you there.